As somebody who taught concrete design 12 times, I'm going to have a hard time going from 28 to 56. You know, you say a number long enough and it's stuck. I'll do my best though, if the change comes about. At this point, I'd like to open the floor to any questions for any presenters. Please jump up, grab a microphone and have at it.
Thank you to all three of you for excellent presentations. Michael, yours was very thought-provoking. And so my question is, just as Bill kind of indicated, owners, everybody who's been in the industry will have a hard time getting around that mindset. But as an owner, what do you do then when it doesn't meet strength at 56 days? Because, you know, by then the superstructure's on the substructure or the bridge deck doesn't meet strength and the contractor's already starting to mobilize away because, you know, they're done with the project. So what are the challenges there?
I think that situation is going to be exceedingly rare. If we keep our current design standards and we're looking at, let's just say a 4,000 PSI design, if you can't hit 4,000 PSI with an approved mix at 56 days, you've got a lot of issues going on. And I think it's kind of hard to say, how do you do it? What would you do? It's almost a case-by-case specific remediation. But this country does not have a concrete strength problem.
Mm-hmm.
And I know that we've heard, as we've moved towards the Portland limestone cements, we've heard some situations around the country about concerns with strength and strength gain. And the ones that we've dug into, we're not seeing any statistically different information for the Portland limestone cement strengths and strength gain versus regular cements that we're used to. Right, there was one that got a lot of attention in one of the Midwestern states, and we went and really dug into it. And we found that the cause of the poor performance was their 0.40 water cement ratio in mixed design ended up being a 0.52 in production. Well, that's got nothing to do with Portland limestone cement or, you know, the strength gain of the concrete or anything else. I mean, that's just bad concrete practice. So you can screw up anything. But I think strength concerns are overblown and generally not warranted.
So is it fair to say that some of the other tests will be indicators of those big issues that would affect strength?
Yes. Yes. In fact, I mentioned if I could, the chemical reactions that give concrete the strength that it gets are the same ones that provide good results in our resistivity testing. And so again, bringing those tests together makes a lot of sense. And again, realizing that concrete, that if we need 4,000 PSI on our abutment to hold up that girder, if we get 4,100, we're just fine.
Thank you.
Yep.
Also, aim this one at Mike, great presentation. So we have been discussing, we in the concrete community, our obsession with compressive strength for as far back as I can remember, and I can remember pretty far back. Why has this not changed? What's the resistance to our obsession with strength?
All right. Well, now that my nephew is out of your class, I can be candid with you. No, why we haven't changed? Look around the room. We're engineers. We don't change anything. And
Bill still uses it in his class?
I gave a presentation last year down in Alabama. I was asked to come, and the ones who really don't change, and I feel very comfortable saying this because I was one for the first 10 years of my career, but the bridge guys. Bridge engineers are the most conservative of our conservative little group here, and they will not change. But I'm down in Alabama, 150 structural engineers in the room. The talk was all about 56 days. I had a bunch more data, all kinds of stuff. I started my talk by saying, how many people think going from 28 to 56 days for compression acceptance is a good idea? Not a hand in the room went up. I went for 45 minutes and it was a good talk and I nailed it. And I asked the same thing at the end and not a hand in the room went up. So believe me, I share the pain. I mean, that is my job, is to get folks to change that. But it is strictly the momentum, because when I talk with agencies one-on-one, they all get it. It's some of the implementation challenges. Connecticut wants to do this. Their engineer told me 2 weeks ago, we would make the change tomorrow. He said, we don't have storage space in our curing room. He says, we got to figure out how to deal with the logistics of sample storage, but we definitely want to do it. It's the right thing to do. And I had, about a month ago, I was out with our trailer in Wisconsin. And the Wisconsin State Materials Engineer, he kind of cornered me and he said, Mike, he said, I got to tell you, you make my blood boil. And he said, he said, I've seen you speak at several conferences and you really pissed me off with this talking, because I also talked about getting rid of the slump test, going to 56 days, and a few of the other things. And he said, you really pissed me off. He says, because you throw it right in our face, these outdated concrete specs we're using. He said, but you can't stop because you know us state agencies, we're not going to change until you guys beat us over the head and make us change. So, I mean, I think it has nothing to do with engineering. It is all human factors and the fact that we're engineers.
Thanks. Andrew, I wanted to hear more about ham, if you don't mind expanding on that a bit. Thanks.
Sure, is this on? Yep. So the entire idea is to take additive manufacturing material, which is inherently not particularly strong, and strengthen it so that we can use it in ways that are more structural, more infrastructural. So the basic idea is to take a reinforced plate of thermoplastic. So it's a thermoplastic plate with reinforcing, usually glass, or it can be carbon, doesn't really matter. And then 3D printing over top of it with a material it's the same material. So then because you have that same material being printed on top, you get molecular diffusion between them, you get shear transfer. So now you basically have what's in essence a reinforced concrete beam. So you have compression on the top, tension on the bottom with something that's good in tension, something that's good in compression. It's better. And also another sort of added benefit about that is now you can actually print overhangs. So for instance, if you see tomorrow or today, or if you've seen it at some point, the 3D printed house that we have out back behind the structure center, it has windows. And the way we made windows was to print the entire thing and then cut out the windows. That's a lot of wasted material. So if we instead put down a plate on top of where the window lintel is and then continue printing, we now have a pre-made window that we didn't have to cut out. All that material is saved. And that's sort of just cool. We can do that. And then with 3D printing, we can print the shape that we want. And then we reinforce it where it needs to be so that we can use material more effectively. So I know you didn't really ask a question, but that's sort of the elevator pitch. You're welcome.
Mike, sorry, I teach my materials lab, and I always struggle with, freeze-thaw, water cement ratio, but of course, low water cement ratio gives you a higher strength. So our specs are, I feel like very often like the magic 0.4 water cement ratio is there, but I feel like we can possibly change that. So anyways, how do we address water cement ratio is that like the resistivity tests will give us kind of the freeze-thaw durability? I guess I'm not very familiar with what are the specs are for resistivity.
Okay, what the resistivity test is, it's an indicator of the porosity of the concrete, how easy it is for salt, water, and other garbage to get into the concrete. So we want a higher number, and for those of you who have been around Maine for a while, it's a very similar technology to the rapid chloride permeability test. It's just a huge technological advancement because it's, instead of 2 days, it's 5 minutes. You don't have a lot of nasty chemicals to get rid of on the back end. It's cheaper. It's just a much better test, but it's an indicator of concrete's ability to resist, garbage getting in. Salts, de-icing salts, and that kind of stuff. Groundwater sulfates, any kind of contaminants. So it's tied to the water cement ratio, but we're starting to move away a little bit from water cement ratio when it comes to project specifications. Because of some of the testing we have available, paste content. Of water with the cement, the total paste content. Paste content is one of the new standards that has come about. Oh, thank you. That is in the ASHTO R101. And if you're not familiar with ASHTO R101, It's kind of known as the performance engineered mixture specification, and it has 6 performance categories. And what we did when we put that together was basically do what the asphalt folks did with Super Pave, is that we looked at where does concrete fail? Now, where does asphalt fail? And I have to say this because I say it everywhere. Where does asphalt fail? Early and often. Right? I'm a concrete guy. All right. So we looked at where does concrete fail, and we looked at 5 failure mechanisms plus the need for workability, and we came up with standards that incorporate the new technologies for that. That wasn't intended to be a cut and paste spec for states. It's more of a mixed design guide and an indicator for states of here are some criteria you may want to put in your spec. That was why we have now developed this durability spec. And I say, rather than try to explain that, shoot me an email. I'd be glad to send you the spec, and you can kind of look and see what the interrelationship is in the spec between things like resistivity, paste content, and water cement ratio. Resistivity, you can get a fully decked out unit for $4 grand. And there's 2 available. There are 2 different types. One is from ProSec. That's a handheld model that has 4 probes that come out. So when you touch it to the cylinder, you have to touch it 4 times all the way around and average your results. Some technicians like that because it fits in your pocket. There's a desktop model that Geotech makes that already has. The surface resistivity test is an absolute no-brainer. I met with the folks from ACI about 6 months ago. They are developing a companion certification. ACI is developing a companion certification to their field level 1. And what they wanted from us and from our trailer program to know is what test do we think should be incorporated into this new certification. We gave them the list. Certainly the resistivity test was on it. And I think with the number of states, again, that have already gone in this direction and others that are on the precipice, I think students would be well served to be exposed to this in an undergraduate environment. And I have visited we have a program where we do campus days. We bring the trailer to campus and do some concrete demos and things. And the things we've seen on campus, more and more campuses are including resistivity at the undergraduate level. Can I ask a question?
Yes.
I've got one, and this has been bugging me for years. Years ago, Ken started bringing in some of these high-tech materials into Maine, and I had some questions, and there's one that I've never gotten answered, and I'm not sure which one of the 2 used the right one, but with the rebar, with this, funky rebar stuff. One of the reasons steel works so good is the coefficient of thermal expansion. And as back in the day, when Ken first exposed me to these things, I did a little reading on them. And my understanding is that a lot of these kind of materials have different thermal properties in different directions. So what is the long-term impact or potential impact on bond and therefore structural performance if we've got 2, thermally different materials?
Yeah, that's a fair question. I've asked myself the same thing. We learned that steel is 6 times 10 to the minus 6 and concrete's 5.5 times 10 to the minus 6 per degree Fahrenheit, and they work together. But I don't actually think that the stresses developed at that interface under thermal cycling are actually that high a lot of the time, if you actually do the calculation. The other thing is that FRP rebar is a lower modulus material, right? It's got a lower E typically. Glass has a much lower E than steel, which means that's not going to develop as much stress as you would if it were a higher modulus material like steel that didn't move with the concrete. And of course, what's out there right now, thermoset rebar, that's accepted, right? We've got ACI code on that. We've got AASHTO code on that. It's used in bridge decks. Maine DOT is using it pretty routinely along with other states. And we haven't seen any effects that I'm aware of related to that so far. So it seems to be performing well in tough environments. This thermoplastic rebar would behave very similarly to thermoset. That CTE is driven by the fiber and the fiber is the same.
Appreciate the insight. Thanks.
Any other questions? Yeah, come on up.
This is also for Michael about the concrete. Yeah, we've been working with the Vermont Agency of Transportation, and you're sort of like preaching to the choir. They're fully adopting or trying to fully adopt the 56 days But one thing that's just come up recently is the notion of shrinkage. They have a spec that the mixes work well for 28 days, but then they continue to shrink up at 56 days. Is there any considerations for shrinkage?
Excellent question. And I mentioned that this AASHTO R101 standard had 5 performance criteria. Shrinkage is one of them. And since we have rolled that out in 2016 and been implementing that around the country, shrinkage has been kind of the forgotten part of the equation. And one of the reasons is when we wrestled with the idea in 2016, but the primary test that we are recommending for this, there's only, I think, 2 labs in the country that have it, one at Oregon State and our Turner Fairbank Research Lab. And so we are rewriting, and we're in the process of it right now, rewriting a bit of R101, and the shrinkage is one of the ones that we're focusing on. Jim Wild has done some great work in Vermont with the shrinkage testing. We've coordinated with Minnesota DOT, who does a lot of work as well. Very interested in the Phoenix. I showed that Phoenix test. We loaned ours to Jim, and they've done some work with it. But I think the answer is going to come just as it came for a number of these other areas, with better technology that comes from our research sector. And there is right now we had a meeting at Turner Fairbank, I'm gonna say 6 months ago. We brought 8 states in and a number of academics along with the concrete industry. And we asked them the question, look, this shrinkage has kind of been the forgotten part of performance engineered mixers. Does anybody care anymore? Agencies, are you gonna specify this? Industry, are you gonna design for it? Or do we just get rid of it? Do we think we don't have a shrinkage problem? We'll get rid of it. And the overwhelming consensus was no, we need it. And one of the things we became aware of is Dr. Anton Schindler at Auburn University is working on a very exciting new shrinkage test, a ton of promise. The Texas DOT is funding the work. And if he didn't get the money from Texas DOT, my office was going to pay for it. Because he showed us this test at this meeting we had down in DC. Everybody in the room, and this is NRMCA, ACPA, American Concrete Paving Association, National Ready Mix Concrete Association, and the 8 DOTs in the room were universally impressed with this test. So I think we do have some good new technologies coming. And I think there's going to be a lot more interest in designing for shrinkage as we move towards this low carbon materials program. I can't say a whole lot about it because we haven't announced the awards yet, but I was on the scoring panel for these proposals that came in. And this is a $2 billion program that Federal Highways is administering kind of jointly with EPA to get states and the private sector to start using low carbon materials in concrete. And there was a lot of discussion in the proposals about some of the materials that they're interested in, and the impact on shrinkage was a key factor. So it's certainly on the forefront. I think it's coming to the forefront again, and the solution is going to be in the better technology that will come in a year or two, which is easy for me to say because I'm retiring in 3 years. So, a year or two, maybe 3, we'll be there. We'll be good.
Any other questions? I've got to ask you one, actually. And understand it's coming from a bridge engineer, all right? So I was before I became an academic, but I've load tested a lot of bridges for the Maine DOT. Many of them older concrete bridges, 30s, 40s, 50s, cast in place T-beams, concrete slabs. And I'm almost invariably amazed by the good condition that they are in. A lot of those bridges, they may not load rate, they may have issues with design. They were designed for H15, the rating factor is 0.6, whatever. That's a problem. That's a different issue. The concrete itself is often in excellent condition. And I always ask myself, being a person, all I know about concrete really is F prime C, right? I'm a bridge engineer. But, I keep thinking, is simpler better? A lot of these were designed around 3,000 PSI mixes, 3,500 PSI mixes. Of course, it would have been Portland cement concrete. We weren't using alternative cementitious materials then. But what I'm wondering is, does this support your contention that, that would have had less cement in it? It would have been a simpler mix. They weren't ending up at a higher strength because they didn't need to target a higher strength. The QC was probably less rigorous, and they were probably getting actual field strengths that were more tightly grouped with the design strength. Now, ASR didn't exist so much back then. We had good aggregate around. That became a problem in the 80s, but does that support, do you think that that's potentially why, that we're moving towards a simpler is better and, you know, that supports your case.
I think that's part of it.
Yeah.
But I think, as I have also thought about that, and I remember riding through Portland with Tom Doe many years ago, looking at bridge condition and talking about that very issue. And because we see older bridges that do tend to perform, the concrete, but as long as ASR didn't get it, the concrete performed
Right.
really well in a lot of older structures in this country. And I am convinced the reason why it goes back to kind of the nature of the hydration reaction. And it's why if we do a concrete bridge and it's 50 degrees and we do it and it's 80 degrees, the 50 degrees is going to have far better performance in the long run. Because as that hydrates, those concrete fingers, they start to grow together. And if we have what I'll say is a more orderly reaction, it's more thorough. We get less unhydrated cement. We get a tighter weave in the fingers. So basically a tighter screen, so it keeps more salt and garbage out. And if we scroll back 50, 60, 70 years, cements are way different today. And one of the biggest differences is the grind.
Okay.
Because today's type 1, what meets standards for today's type 1 was yesterday's type 3.
Hmm.
And because only 15% of the concrete in this country goes to infrastructure, we're the small player. We can't do what we did with Superpave. We were the big gorilla with Superpave. When we said this is going to happen, this is going to happen. With 85% of the concrete going somewhere else, the changes we want to make happen, they've got to make sense to the concrete industry as well. But because they've driven these, it's been the speed of construction necessary for the private sector. They've got to get those form strips so they can build the next layer of that high rise, or they got to build the next house, or, wherever it's going. And I think the fineness of the grind, because back in the old days, cement particles are much larger, they reacted much more slowly, and I think we got a much more thorough, complete reaction that resulted in more durable concrete. Because we see a lot of the problems, it's no different than, comparing a concrete with an accelerator.
Well,
You
yeah,
lose performance in the long run when you use an accelerator.
right. And I mean, that's another thing I always think about. We put a lot of stuff in concrete we didn't used to put in it. I really there's very complex chemical reactions happening there. And I don't think we fully understand all of it either, but I had not thought of that because I don't know enough about concrete, but that's a good point. So we're using yesterday's higher strength concrete right now. Yeah. Okay.
Along with yesterday's specifications.
Right. Okay. Okay. Any other questions out there? Yep.
Let's talk about conventional fatigue and how that compared to your composite.
Yeah, I'll try to touch on that. So I didn't want to dive into too much detail during that explanation, right? But what we had in that girder we tested, we had ply drops in the bottom flange. So we've got more carbon near midspan where we need it, and we drop it towards the supports where moments get lower, okay? And we actually designed that test to assess that ply drop. It didn't actually fail there, which is a good thing, okay? But that means two things. Number one, it means we actually overloaded that girder. When I said we did a fatigue 1, AASHTO fatigue 1, we were actually 15 or 20% above the AASHTO fatigue 1 stress level between the load heads, okay? And it actually failed at a load head where we had a shear suddenly occurring that was about 2 times the size, 2 times the magnitude of a maximum legal truck axle on a truck, okay? So we had a lot going on there that made that test conservative, and that's okay for the first time we do it. When we look at steel, we saw that ply drop, and that's what we were trying to assess. And I took that as analogous to, a cover plate width or thickness transition, right? Which is an AASHTO fatigue category B with the right grind on the weld. And I based the 3 million cycles because that's basically the endurance limit for a fatigue 2 test for a steel plate girder with a thickness transition in the bottom flange. So there's no standard for FRP, right? We have to look at similarities with other materials in AASHTO and design a test around that to fit our girder. Hopefully that answers your question.
And also on the fiberglass rebar, it seems like that's closer to concrete on linear expansion than steel, some of the fiberglass. Maybe Andrew, is that true?
I mean, I do not know that for certain. I've looked a little bit at expansion for FRP, and it tends to be around that area, but I don't want to say blanketly that it's definitely exactly that.
Yeah.
Might help
Yeah, yeah, and, you know, carbon's the one that can actually go the other way sometimes, right? So, but then again, you know, we do use carbon reinforcing as well, and there haven't really been any issues that I'm aware of long-term, although we don't use it as often, that's for sure. Yeah. Any other questions? Okay, well, thanks everybody for sticking around to the end of the day. I want to thank the panelists for the conversation. That certainly was thought-provoking, really interesting.